We've been talking about electron configurations for neutral atoms, but in reality, we rarely deal with neutral atoms. We almost always have elements that are in compounds, and often they are in ions, and it's the electrons in the ions that are interacting to form the bonds, just as it's the electrons in the valence shell of the atoms that are forming covalent bonds too. So let's spend some time looking at electron configurations of atoms as they are forming ions. So let's think about a familiar compound like sodium chloride. We know that this is an ionic compound from earlier work, and we know that it is sodium plus and chloride minus. So if we look at the electron configuration for neutral sodium, if we pull out our periodic table, which you should find that the sodium electron configuration for the neutral atom is 3s1, and for chlorine, the neutral atom is neon 3s2, 3p5. When a neutral atom like sodium loses an electron, then we're going to take it out of the highest energy orbital. That highest energy subshell is the valence shell. These are also valence electrons. And this is where we add or where we remove electrons. So if sodium loses an electron, it's going to lose this 3s1 electron. And so that means that the electron configuration for sodium plus is just going to be the same as the electron configuration for neon. This is a noble gas electron configuration. The chlorine is going to gain an electron, and so it will become chloride. And so if we look at this, we'll see that the one spot we have to put an electron is here. We have 3p, and we have 5 electrons that are currently in that 3p subshell. So we have space for one more electron right here. So that's going to be 3p6. But notice that this is also exactly the same thing as the argon electron configuration. So both the sodium ion and the chloride ion have reached a noble gas electron configuration, and noble gas electron configurations are extra stable. And when we say that something is stable, what we mean is that it is energetically favorable and that it is a lower energy configuration than the previous version. So you will notice that when we have a monatomic ion and we make ions out of it, or we have an atom that makes a monatomic ion, it will almost always be a noble gas electron configuration, at least for the main group elements. So the main group elements are the S block and the P block of the periodic table. This is called the main group. All right, let's try this again. So let's take a look at magnesium oxide. We know that these, from our study of these compounds, will be the Mg2 plus ion and the O2 minus ion. So go ahead and take a second here and write out the electron configuration for the neutral atom and then turn it into the ion, and do the same thing for the oxygen atom and the oxide ion. Pause the video and give that a try. Okay, welcome back. So hopefully you noticed that this also is neon core with 3s2 electrons in its valence shell, and those two 3s2 electrons are going to be the ones that are removed. And so this will be our neon noble gas electron configuration. So the oxygen starts out with a helium core, and it is 2s2, 2p4 for its electron configuration. It gains 2 more electrons. Here's those 2p. We have 4 electrons, which means that we have 2 spots available. So those are where we're going to put those extra 2 electrons, which means that we will end up also with a neon electron configuration. So another term that we need to talk about is one that is isoelectronic. You might remember from our conversations about gases that isothermal meant constant temperature. Iso really means the same. So isoelectronic means the same number of electrons. And if these two atoms have the same electron configuration, that means that they are isoelectronic. They have the same number of electrons. And let's double check. Well, yeah, if we had magnesium had, let's take a look at a periodic table. All right, here we go. So magnesium had 12 electrons, and then we removed 2, so it has 10, like neon. Oxygen had 8 electrons, and we gave it 2 more, and now it has 10, like neon. So these are isoelectronic. It's pretty easy with group 1 and group 2 elements to see what their noble gas electron, what their ion electron configuration is going to be, because we just have our valence electrons in the s orbitals. We lose whatever electrons are in the s orbital, and they are always going to have that noble gas electron configuration of whatever the noble gas is that comes right before that element. The same thing is true for these nonmetals over here that are forming anions, that they are going to get enough electrons to make them have the noble gas electron configuration that's over here to the right of them. So oxygen will become neon in its electron configuration only, doesn't change the number of protons. Sulfur will gain 2 to have an argon electron configuration, etc. It's a little bit harder to see what's going to happen when we are looking at the transition metals. So let's spend some time talking about the transition metals. We could really go down a rabbit hole with transition metal electron configurations, because although we have some sort of standard rules for looking at electron configurations, we do get some sort of weird exceptions in here every now and then. The same thing is true in the D block, in the F block here, that it's not just about the transition metals, but also about the lanthanides and actinides. There are some strange exceptions to what we consider our rules. They aren't really rules, though, for electron configurations. They're more just kind of observations. Okay, so we're going to spend time talking only about the first row of transition metals, because there are 2 important exceptions for us to look at that illustrate what the rest of the exceptions are going to be about. So you do not need to know the electron configurations for the transition metals past this first row. These are the only ones that we'll be worrying about. So let's take a look at them. Let's pick, for example, an iron compound. Let's look at iron chloride. But first, let's look at how many valence electrons iron has in its neutral state, and then we'll be ready to go. So let's see. We have iron. It's going to be in this 1, 2, 3, 4th row. So that means that it has an argon core. And then these 2 electrons will be 4s2, and then we go to 3d. So we have 1, 2, 3, 4, 5, 6 electrons in the 3d subshell. So let's write that out. So neutral iron, we decided, had an argon core, and then it had 4s2, 3d6. Now, you may also see this electron configuration for neutral iron be written as argon 3d6, oops, not another bracket, just 4s2. And the reason why this is the case is actually going to lead right into our conversation about ions, and so it's worth our time to talk about them. So the reason why these orbitals are listed with the 3d6 first and then the 4s2 is that we have something interesting happen to those energy levels when we put electrons in our orbitals. So here's our relative energy level. So with no electrons in the orbitals, we have our 4s energy level, and then we have our 3d energy levels like this. And anytime we have multiple energy levels that are all the same, we say that they are degenerate. And that's just another special term that you may hear, so I want to make sure you hear it. And it just means multiple orbitals with the same energy. Okay, so this is where we have no electrons in these orbitals. As soon as we put electrons in these orbitals, then what happens is that the 4s orbital actually ends up slightly higher in energy than the 3d orbital. So this is with electrons in it. So if we were thinking about the iron, then this would be the orbitals before we put the electrons in, but once we put those electrons in, then those 2 4s electrons are actually higher than all of those 3d electrons. Let's see, we have 6. So yeah, 2, 4, 6 3d electrons. Also notice that these electrons are going to preferentially not pair, and that's because electrons repel each other. So they preferentially unpair, and they only pair up if they absolutely have to, because otherwise there's this electron-electron repulsion energy that we have to overcome. So it takes less energy to put these electrons in separate orbitals than to pair them up. All right, so what this means is that when we take electrons away to make, for example, if we have FeCl3, we know that this will then be an iron 3 plus cation. So if we're going to make an iron 3 plus cation, we need to take away 3 electrons. So we're going to take away the highest energy electrons. We're going to take away the 2 of them that are in this 4s orbital, and then we're going to take away one of the ones that is paired up here. So our after electron configuration is going to be still the argon core, but we will only have 3d5 for the rest of our electron configuration. So that means that our Fe3 plus electron configuration, if we wanted to do an orbital diagram, this 3d5 would be 5 unpaired electrons. And we also refer to this as a half full D subshell, because the D subshell has room for 10 electrons, and since there's only 5, that would be halfway full. All right, so let's take a look at the electron configurations for all of the transition metals in that first row, in the 3D set of subshells. we'll actually just go ahead and start with potassium and go all the way through to zinc. And that way we can look at any exceptions that come up. Okay, so potassium we know has an argon core and one additional electron. And I'm going to go ahead and draw our orbitals just so we can kind of visualize. We're going to have, they're not the same energy, but just for space issues, I'm going to put them next to each other as though they were. So for calcium, now we have 2 electrons. And so those are both going to be in the 4s because right now the 3d orbitals are still a little higher in energy. Next is scandium. These will all have the argon core, and then we will have 1 electron in our 3ds. And we just routinely put it in the first one. It doesn't really matter, you can put it anywhere you want, because there's just 1. The important thing is that as we start adding more electrons into that d orbital, that we don't pair them up. All of these will have unpaired electrons, as many unpaired electrons as possible. The s subshell does have these paired up, but these d orbitals don't. All right, so 4s2, 3d3. And I told you that the s orbitals are paired and the d orbitals are not until we have to, and that's true until we get to our first exception. And our first exception is chromium. So chromium, if we're following this pattern, we would expect that the orbitals, or that the electron configuration would be argon, 4s2, 3d4, right? That's what we would expect. But that is not actually what happens. Instead, chromium has an electron configuration of 4s1, 3d5. We have 6 total electrons. We have 1 electron in the 4s, and we have 1 each in each of those 3d orbitals. So this turns out to be lower energy to let that 4s previously paired up electron unpair itself into the 3d shell. Okay, so this is our exception. But then we move on to manganese, and we're back to normal. Of course, manganese already has that half-full subshell of the 3d because now it has 7 electrons. So here's our paired up s, and then we have unpaired d orbitals. But we're back to normal. So we already did iron, but we'll put it in our list just for completeness. 4s2, 3d6, everything normal. I always will put in my spin up electrons before I start pairing them up, just to remind myself that my electrons should be unpaired if possible, and I will only pair them up if I have to. So that's why I do it that way. Our next element is cobalt. 4s2, 3d7. No strangeness here. There, I just did it the other way. There we go. Nickel is next. 3d8, so there's our paired up s. 1, that's a little too far over. 1, 2, 3, 4, 5, 6, 7, 8. So now guess what's going to happen with copper? Copper looks like we're going to have 4s2 3d9, right? But it's going to do the same thing as chromium. We're going to have an exception here too. So just like with chromium, we are going to spread out one of these s orbital electrons and make a full shell. It turns out that the fully filled D shell is also extra stable. So there is a special stability with the half full shell, subshell, and with the fully filled subshell. These are extra stable. So they are energetically favorable for us to do. So chromium and copper are the two exceptions in the first row transition metals. Zinc is full, 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 so it has no options here. 4s2, 3d10, everybody is full. So all of the subshells are full for zinc. So if you look at a table of electron configurations for neutral atoms, you will find other exceptions there too. In fact, the further down you look in the D block and the F block, the more exceptions you will find. Most of them have to do something with these kinds of exceptions, a half-full subshell or a fully filled subshell in the D or the F. You are not responsible for worrying about all of those extra exceptions. If you ever need to know what they are, then you just look them up. It's no problem. But these are the two exceptions I would like you to remember, and everything else is just normal. So let's go ahead and spend a tiny bit more time practicing doing electron configurations of ions before we finish up. So let's practice with copper plus, copper 2 plus, cobalt 3 plus, titanium 2 plus, and how about chromium 5 plus, just for fun. All right, so pause the video and give these a try, and then I will write down the answers for you to check. All right, here's for checking. Remember that we are taking electrons out of the s orbital first. So copper plus has 1 electron in the s orbital, so we would end up with argon 3d10. Copper 2 plus, we've already taken all of the electrons out of the 4s orbital, so now we need to start taking them out of this D, even though it breaks up our fully filled subshell. Cobalt 3 plus, we take those 2 electrons out of the s orbital, and we end up with 3d6. Titanium 2 plus, we take the 2 electrons out of the s instead of the d, just as before. So we're always going to end up with d electrons. Taking 5 electrons away from chromium leaves us with just 1 electron in the 3d orbital of chromium. Okay, so hopefully this has been a good practice on learning how to deal with electron configurations of ions, and please make sure to ask if you have any questions.